Hey y'all, we're checking out geometric series today, and last time we met we were looking at arithmetic series, which is taking a set of numbers like 3 and 5 and 7, right? That's arithmetic because you're adding the same thing and adding them all up, right? Up to dot 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 some other spot, yeah? And adding those all up, the s from S to the N, right? And all of these were arithmetic because you were adding something to get the same thing to get to the next one. We're going to do the same thing, but with geometric sequences. Adding them up makes them a geometric series. So this little cartoon over here is about that, right? He sees that haircuts are half off when he goes in, and they take half of his fur off. So he goes back in, and they take another half of his fur off, right? And when he goes back in, they'll take half of that, and then half of that, and then half of that. And it should literally take forever. So buckle in. We're going to check out some geometric series. One way to do this is just brute force add them up, right? So is this geometric? Yeah, we were multiplying by 3, multiplying by 3, right? Multiplying by 3. And if we want to find the series, which is the sum up to the 12 terms, we can just multiply by 3 and get the next one, multiply by 3 and get the next one, all the way to the 12th term, and then add them up. And man, that's horrendous. There's got to be a better way. And there is. The equation looks like this. Ping! Like that. And if you want to just roll with it, then fast forward me until you see a great big smiley face like this, because you'll know that my derivation is done. So I'm going to do a derivation for you. If you're interested, I think it's really neat to see where these things come from. If you're not interested and you just want, I think it also helps you remember the formula. But if you don't want to see it and you're cruising, go for it. You can put me in fast forward chipmunk mode, but here goes. Here's the derivation. If we list a series out, we're just adding pieces up, right? So we start with some term A, and we don't multiply anything by it. So this is basically 1, right? And our next term is A, and we multiply by the ratio once. The next term is A multiplied by the ratio twice, etc., up to 1 less than the term number we want, right? So we start out like this. Now, I'm going to just take it and color-code it briefly. Just the explanation will be a little easier. So it's the same thing. It's just color-coded so we can see it, and I'm going to hide this from you just so we don't get too set on it. Nice. The awful thing about this is that this, well, one of the awful things about it is that this has a n minus 1 as an exponent, and that's no fun to work with. What would be really nice if we multiplied this whole side by an r and multiply this whole side by an r. And what that'll do for us is this. If you multiply this in, now you have a times r minus 1 times another r. This will all become n, a to the r, a times r to the n. But you have to do it to all of these. So what's going to happen to these is if you multiply r here, instead of having r to the 0, this will become r, and this will become r squared, and this will become r cubed, etc., all the way up. Everything's going to increase by 1 its exponent, and it'll look like this. Right, so I'm going to delete these pieces because we're going to need them in a second. We fundamentally haven't changed the equation. It's like saying 2x equals 6, and if we multiply both sides by 3, you still get a true equation. We haven't changed anything. We're still fine. So if we multiply both sides by r, it shows up here, and this term turns into the r to the first. This term turns into r squared. This term turns into r cubed, etc., etc. And this r to the n minus 2 turns into n minus 1, and this turns into n, which is nice. We did all that work for this. If you subtract these two equations, what's neat about that is this will turn into this sort of thing. If you subtract the series minus r times the series, you'll end up with this piece. That's not necessarily anything swell, but this, if you subtract these, this will give you a times r to the 0 minus the 0, gives you this exact thing. This is a times r to the first minus itself gives you 0. This gives you 0. This gives you 0. Ad finitum here until the n minus 1. And then also you have this 0 here, and when you subtract that, this piece gives you negative a times r to the n, right? So if you subtract these pieces, you end up with another true equation that basically says this. This is a, right, minus a times r to the n. If you clean that piece up, this is the left side. We factor out an Sn, right? And here's the 1 from this, here's the r from this. And on this side, you're left with a times 1 and a times r to the n, right? All of this stuff kind of goes away. If you clean that up a little more, you pull an a out and do a little cleaning work, you end up with this. Here's our s to the n. We've divided this off of both sides, and it ends up in the denominator here. We've factored out an a. It looks like that. If you clean it up a little more, you can change a for u sub 1, and it'll look like that, right? And that's the equation that we're going to use. Huge smiley face to let you know that we're done with the derivation. Everybody's done with the derivation. We love being done with the derivation. So let's go from there. We're going to use that whole idea and try it with this. So this is a finite geometric series, and we want to find the sum. It's the same thing that we were going to just manually add up, but we know that we're going to use this piece is the first term, right? That's the first term. Both of these r's are the ratio from one to the next. So in this case, it's going to be 3. And this n is going to be this, the number of terms, how many terms we add up. So n is going to be 12, right? U1 is going to be 2 from here, and r is going to be 3. If we plug that all in, oh, there, they got it written for us. They plug it all in, and it should look like this. Here's the first term, here's the ratios, here's the 12. They're using the same thing. You can write this a different way with this flipped around. If you factor out a -1 out of each of these, I think both of these are in your formula booklets. There's the exact same formula can be written as u1 and r to the n minus 1 over r minus 1. All you're doing is dividing top and bottom by -1. It flips the signs in there, and therefore you can flip the pieces. It doesn't matter which one you use. I like this one because I can derive it if I forget it. But it doesn't really matter. So plug in the pieces that you know, and you should end up with this at the bottom. Give it a shot, make sure you can do it, and let's try this next one. All right. You've seen Russian nesting dolls. They kind of fit into each other. They're just so full of themselves. I like this one too. It's like an infinite screenshot taking an ultrasound of one of these because you can see each other. All right. Go away. There you go. So you got 10 of them. They're each 5/6 the height of the previous one. The first one is 15 centimeters tall. What's the total height if you laid them out end to end like that, right? Great. Well, we know a couple of pieces, one of which is that we have the first doll is 15, so that's this piece. We know that there are 10 of them, so that's that piece, and we know the height is 5/6 of the previous. So U1 is 15. What R is 5/6, and N is 10. All right, plug and chug. Give it a shot. Ooh, ugly formatting, but you should get to 75 centimeters. Try it out. All right. You can do the same thing with this. If you want to pause and try it yourself, be careful that the R is going to be negative on this one, and see if you can wrestle through the fractions. Go. Cool. This ends up with, they wanted you to find the formula, right? So you don't end up with an actual number, but you've ended up with this piece. Hopefully you cleaned this up because it's prettier that way. Great. So those are all finite geometric series. There are infinite geometric series as well, but we can contend with those. This is a divergent series. What that means is as you go from one term to the next, yep, it's multiplied by 3. Why is it so big? There we go. Multiply by 3, multiply by 3, right? It just gets bigger and bigger and bigger. And as you add them up, your number your sum gets bigger and bigger and bigger. So the series diverges, doesn't come to an end, right? It's not worth talking about. However, if your some series like half now goes to a fourth, now it goes to an eighth, now it goes to a 16th, we're multiplying by a half. We're dividing by 2, right? And if you have a ratio, an R term, that's less than 1, bigger than 0, it's fractional, if you'd like to think about it that way, you have a convergent series, which means that this gets smaller, but eventually you're adding such small pieces that it's not worth talking about, the change in the sum. Let me give you a visual example of this. This is one whole square, right? We call this 1. So this piece in the middle, or this highlighted piece, that's 1/2, right? It's half of that. So I'm representing this visually. So great, let's remove these. If you add to that, if you cut this in half, half of this half is a quarter, right? Half of that half is a quarter. So now we've gone half plus a quarter, right? So now we've got 3/4. Yay. If you add half of that quarter, right? Half of that quarter is an eighth. Yeah, so here's an eighth. If we add half of the eighth now, we've got a 16th. It keeps being a smaller piece. If you add half of the 16th, it's a 32nd, and then it's a 64th, and then it's a whatever. It keeps getting smaller and smaller and smaller, and eventually you're adding such small pieces that they're not changing the value of the sum. And in essence, if you do this, if you try this and go and go and go and go past 1/64th, you'll find you never ever surpass 1 whole. And that's partially where this convergent series equation comes from. And it works like this, that this is the first term, as you would expect, and this R is just the ratio. In this case, it's 1/2, right? And so you can figure out what the total should be. It seems like it should be a whole, but if you throw in the numbers, you can see that it is in fact a whole by doing this. We started with 1/2, right? And we divide by 1 minus the change, right? So now this is 1/2 divided by half, right? Which is really like saying half times 2, which is 1. So that's the theoretical, it's not theoretical, that's the limit that it'll never surpass, is 1. And we can visually see it here. Okay, so let's try that with a little bit of an uglier number. How about this guy? Find the infinite sum of the sequence, 12, -3, 3/4, 3/16. So A is another way to say U1, so it's right here. Here's A. Here's the equation if you need it again. What's R? Well, it's how we go from here to here. It's how we go from here to here. It's how we go from here to here. And if you divide the two, you'll get -1/4. So it is negative, but the absolute value has to be be fractional. And so if you multiply by -1/4, the sign flops back and forth, but it does get smaller and smaller and smaller. So as you add, it doesn't really matter if it's negative or positive. It doesn't change the sum. So we're going to throw those pieces into the equation. Oh, that equation's awful. But let's use this one, right? So we're going to say U1, the sum should be U1 over 1 minus R, which is -1/4. And if you clean that up, you should end up with 12 over 5/4, and you clean that up and you end up with something like 9.6, right? And that's if you add all these terms infinitely. You don't just stop when you get bored, but you go forever. It'll never reach that point. Great, fine. If you'd like to try that again, check this out. It's the same sort of thing. Show why the sum will not exceed 130. This is a common IB question, and you just expect to run through this. Use this piece and show that once you get S, it's going to be less than 130. And so you can fast forward me if you got it, but find the change here. This is the original. This is the U1. And so you're going to end up with this piece, 96 over 1 minus 1/4, because if you divide one by the other, you get 1/4, 1/4. If you clean that up, you get 96 over 3/4, etc., etc., and this ends up being 128, and which does not exceed 130. So we showed that. Yay! Great. Same deal. If you'd like to try that, there's some solutions. And this one I've seen often on the exams, write 0.7 repeating as a rational number. I think this one's kind of neat because it's just sort of tricky, right? 0.7777 means 0.7 plus 0.07 plus 0.007. You get the idea. Get out of here, G, etc. Going on. And if you write those out, this is 7/10, right? This is this one. This is 7/100, that one. This is this one, 7,000ths. And you can see that each time you're multiplying by 1 over 10 to add the next one, right? So you can figure out that your initial value is 7/10, it's this one, and each time you're multiplying by 1/10 to get to the next one, right? It's getting 1/10 as big. And so you plug it all in, 7/10 minus 1 over 1 minus 1/10, and you end up with 7/9, which is the fractional form of this repeating decimal. If you plug 7/9 in your calculator, you get 0.77777. Neat. All right, so that's it. An infinite number of mathematicians walk into a bar. The first one orders a soda. The second one orders half a soda. The third, a quarter of a soda. The bartender said, "You're all idiots," and pours 2 sodas. You can calculate why that's funny and tell it to the friends that you don't have anymore. All right. I'd like you to attack the geometric series homework, and we'll see you later. Okay, bye.